Welcome to the lecture of Renewable Energy System. In today's lecture, we will discuss about the geothermal energy system. Geothermal energy is heat which is gathered from earth. It can be classified into four basic forms. That is geothermal energy, ground source heat pumping technology, aquifer thermal energy storage, and heat pumps. Deep geothermal energy typically from more than 1 kilometer below the earth's surface, which draws heat from hot rocks or aquifer. Ground source heat pumping technology is technically shallow, about 40 meters depth, geothermal energy and utilize the flow of heat between the air and the top layer of the ground. Aquifer thermal energy storage is also shallow, about 100 meters, acting as a geothermal heat pump technology and uses heat flows to and from underground aquifer. Heat pumps can be used with deep geothermal wells to raise the temperature of water up to a usable level for heating buildings. About half of all geothermal energy produced is deep geothermal, used to produce electricity in about 25 countries. These countries are located in areas with volcanic activity that provide hotspots of steam, hot water, and springs. Geothermal energy is primarily used for electricity generation. At a few locations, geothermal heat is available at temperatures of more than 150 degrees Celsius as a natural flow of high pressure water and or steam, so having the potential for electrical power production from turbines. The average geothermal heat flow at the Earth's surface is only 0.06 watt per meter square, with the average temperature gradient of 25 to 30 degrees Celsius per kilometer. This continuous heat current is trivial compared with other renewable supplies in the above surface environment, that in total average about 500 watt per meter square. However, at certain specific locations, increased temperature gradients occur indicating significant geothermal resources. Regions of geothermal potential generally have penetrable rocks of area about 20 square kilometer and depth about 5 kilometer, through which water may circulate. Consequently, they can be harnessed at flux of 10 to 20 watt per meter square to produce about 100 megawatt thermal energy per kilometer square in commercial supplies for at least 20 years of operation. Regions of hot dry rocks have to be fractured artificially to become permeable so that water may be circulated through the fracture to extract the heat. Geothermal information have been obtained from mining, oil exploration, and geological surveys. Therefore, some geothermal information is available for most countries. The most important parameter is temperature gradient. Accurate measurement depends on leaving the drill holes undisturbed for many weeks so that temperature equilibrium is re-established after drilling. Deep drilled survey wells commonly reach depth of 6 km, and the technology is available to drill to 15 km or more. The large cost of these survey wells is partially why the suspected high-grade geothermal potential of many developing countries has not yet been properly explored. Lower grade heat does not require such detailed assessment before it can be exploited. The principal components of a geothermal energy plant are the boreholes, so heat extraction from depth to 15 km may be contrived eventually. There are three classes of global geothermal region. The number one, hyperthermal. The temperature gradient is greater than 80 degrees Celsius per kilometer. These regions are usually on tectonic plate boundaries. The first such region to be tapped for electricity generation was in 1904 in Italy. Nearly all geothermal power stations are in such areas. The second region is semi-thermal, in which temperature gradient is about 40 degrees Celsius per kilometer to 80 degrees Celsius per kilometer. Such regions are associated generally with anomalies away from the plate boundaries. Heat attraction is from harnessing natural aquifer or fracturing dry rocks. A well-known example is the geothermal district heating system for houses in Paris. Number 3 region is normal, in which the temperature gradient is less than 40 degrees Celsius per kilometer. These remaining regions are associated with average geothermal conductive heat flows at about 0.06 watt per meter square. It is unlikely that these areas can ever supply geothermal heat at prices competitive to or present or future energy supplies. In each class, it is in principle possible for heat to be obtained by the following: natural hydrothermal circulation, in which water penetrates to deep aquifer to be heated to dry steam, vapors or liquid mixtures or hot water. Emission of each type may be absorbed in nature. If pressure increases by steam formation at deep level, hot spring may occur. Note, however, that liquid water is ejected and not steam. Hot igneous system associated with heat from semi-molten magma that solidify to lava. The first power plant using this source was the 3 megawatt station in Hawaii, completed in 1982. The third classification is dry rock fracturing. Poorly conducting dry rocks, for example granite, stores heat over millions of years with a subsequent increase in temperature. Artificial fracturing from boreholes enables water to be pumped through the rocks so that in principle the heat can be extracted. In practice, geothermal energy plants in hyperthermal regions are associated with natural hydrothermal systems. In semi-thermal regions, both hydrothermal and perhaps hot rock extraction may be developed. Normal areas have too small a temperature gradient for commercial interest, except for near-surface heat pumps. Geothermal power arises from heat sources having a great range of temperature. In general, available temperatures are much lower than from furnaces. Therefore, although much energy is accessible, the thermodynamic quality is poor. The heat from geothermal sources tend to be available at significantly lower temperature than heat from the fuel. Therefore, the efficiency of electricity generation is less. Nevertheless, exporting energy via electricity network is convenient and often meet national needs. Electricity generation will probably be attractive if the source temperature is greater than 300 degrees Celsius and unattractive if it is less than 150 degrees Celsius. Nevertheless, the energy demand for energy at less than 100 degrees Celsius is usually greater than that for electricity, and so the use of geothermal energy as heat is important, even when the geothermal resource is not good enough for electricity generation. Several factors fix the scales of geothermal energy use. The dominant costs are capital cost, especially for the boreholes, whose cost increase exponentially with depth. Since temperature increases with depth, the value of the energy increases with temperatures. Most schemes settles on optimum borehole depth of about 5 km. Consequently, the scale of the energy supply output is usually greater than 100 megawatt. That is electricity and heat for high temperature and heat only for low temperature. The total amount of heat extractable from a geothermal source can be increased by re-injecting the partially cooled water from the above ground heat exchanger back into the reservoir, but at significant cost. The most successful geothermal projects have boreholes sunk into natural water channel in the hyperthermal region as shown in this diagram. Similar methods are used for extraction from hot aquifer in semi-thermal region, where natural convection can be established from the borehole without extra pumping. The simplest deep geothermal energy extraction method is a deep bore of about 5 km depth. The hot water or steam stored in aquifer pumped up and used for electricity production. Deep geothermal energy need three things for success: an aquifer of sufficiently hot water that can be drilled into, a cap rock to retain the geothermal fluid and a heat source. Aquifer contains porous rock that can store water and through which water will flow. Up to 5 km depth, the water or steam temperature can be to 80 degrees Celsius. Hot water which has been in contact with rocks tend to contain high amount of dissolved solid and dissolved gases and thus can be quite reactive. These contaminated water are called brines and need treatment before being used in geothermal plants. On way to avoid One way to avoid using brines directly is to use the geothermal water to heat clean water or some other secondary fluid for use in the plant, although this incurs losses. The most important rock property within the aquifer includes grain size, shape, and porosity. How these interact with each other also determines site potential along with any fractures or weaknesses in the layer of the rock. The fluid pressure gradients and volume of water flowing in the rock are also key considerations, and systems are measured in hydraulic conductivities. Fluid pressure can reach up to 10 megapascal. Cap rocks are simply impermeable rock layer which ensure the aquifer do not escape. Different rock types have different rates of heat conduction, but in general, rocks are poor conductors. Sources of hot dry rocks are much more abundant than hydrothermal regions. Through them, temperatures of 300 degrees Celsius are accessible under a significant proportion of the world land mass. In this enhanced geothermal extraction technique, rocks are fractured and pressurized cold water is injected in the boreholes as shown in the diagram. The depth of boreholes can goes up to 7 km. The pressurized cold water then reaches the end of boreholes, become the steam due to the hot rock. This steam returns through the shallow return pipe. Using such enhanced geothermal complex arrays of injection and returns boreholes might, in principle, enable gigawatt supplies of heat to be obtained. However, it has proved difficult to constrain the fracturing so that a large enough fraction of the injected water emerge from the outflow pipe. The injected water leaks into other fractures and is lost. These technical difficulties and large costs have limited development to only a few pilot plants, mainly in Europe and the USA. The choice of the heat exchange and turbine system for a particular geothermal source is complex, requiring specialist experience. There are four main types of geothermal energy conversion system. In all methods, nearly always the emerging bore water after use is re-injected into the reservoir. The simplest system passes dry steam from the ground directly into steam turbine as shown in the diagram. This type of system is ideal for vapor dominated resources where steam production is not contaminated with liquid. The system configuration is essentially the same as the conventional fossil fueled steam power plant. The reservoir produces superheated dry steam come out of the ground typically at 180 to 225 degrees Celsius and 4 to 8 megapascal pressure, reaching the surface at several hundred kilometers per hour, and if vented to the atmosphere, sounding like a jet engine at close proximity. Passing through the turbine, the steam expands, causing the blades and shaft to rotate and hence generate power. In the simplest form of power plant, a back pressure unit, the low pressure exhaust system is vented directly to the atmosphere. Although such units are simple, they are also very inefficient. The system efficiency is improved by adding condensing unit. At temperature typical geothermal fluid efficiencies are low. High temperature of 300 to 350 degrees Celsius and higher pressure can produce higher efficiency. But despite use of high temperature, superheated steam rarely exceed 20% efficiency. In early installation of dry steam power plant, very little spent fluid was re-injected back into the reservoir. This causes the fluid pressure to fall. Later, re-injection policy was introduced to make the resource more sustainable, and some 70% of the mass of produced steam is now re-injected and field production has been stabilized. Not all of the field comes from the condensed steam from the turbine because much is evaporated from the cooling tower. Instead, in a new imaginative environment development, treating sewage water is piped from a local community, thereby solving a local disposable disposal problem as well as helping to maintain the thermal geothermal reservoir. The boiling point of water increases with pressure. Thus, if geothermal fluid is drawn from a deep aquifer where it is present as a liquid water, it may boil on the way to the surface as the pressure is reduced. The process of steam production associated with pressure reduction is called flashing. The steam may arrive at the surface as wet steam containing droplets of water, and steam must first be separated from this water in the plant. The separator also has the important function of protecting the steam turbine from a massive influx of water should condition in the well change. However, it is usually better to about flushing in the well because this can lead to a rapid buildup of scale deposit as minerals dissolve in the fluid come out of solution, leading to the plunging of the well. For this reason, the well is often kept under pressure to maintain the fluid as liquid water and the actual flushing to steam take place within the power plant. To deal with hot high pressure water requires complex equipment designed to reduce the pressure in a controllable manner and induce flashing. Again, a conventional condensing steam turbine is at the heart of the plant, but lower steam pressure and temperature of about zero point 0.5 to zero point 0.6 megapascal and 155 to 165 degrees Celsius are common. So the plant typically requires more steam per kilowatt hour than would be required in a dry steam plant, say around 8 kilogram per kilowatt hour. Moreover, the bulk of fluid production or produced often up to 80% main remains as unflushed hot brine which is then re-injected unless there are local direct use heating application available. In general, therefore, re-injection well must be available for the fluid disposal at single flash plant. In single flash plant, this this type of power plant uses a secondary working fluid with a lower boiling point than water, such as pentane or butane, which is vaporized and used to drive the turbine. It is more commonly known as an organic Rankine cycle plant or binary cycle power plant. Its main advantage is that low temperature resources can be developed where single flash systems have proved unsatisfactory. Moreover, chemically impure geothermal fluids can be exploited, especially if they are kept under pressure so that no flashing ever takes place. The geothermal brine is pumped at reservoir pressure through a heat exchanging unit and is then re-injected. The surface loop is closed and no emission to the environment need occur. Ideally, the thermal energy supplied is adequate to rise the temperature of the secondary fluid to well above its boiling point. For geothermal fluid temperature below about 170 degrees Celsius, higher generating efficiency is possible than in low temperature flush steam point. A disadvantage is that keeping the geothermal fluid under pressure and repressurizing the secondary fluid can consume some 30% of the overall power output of the system because large pumps are required. Another disadvantage would be that it requires large volume of geothermal fluid, for example, around 700 kg per second, to produce about 29 megawatt electrical power. Nearly 250 binary cycle units are in operation. The units are often small of about 5 to 10 megawatt. When large systems are required, multiple sets are installed. Some of the countries that are exploiting geothermal resources for non-electrical purpose have chosen to develop these direct use applications in areas flanking the main steam field. Japan, New Zealand, Iceland, and Italy are the example where wet steam or warm water at a range of temperature is readily available for industrial and domestic application. Direct use is the oldest form of geothermal energy development by mankind. Different categories of direct use exist, for example, space and district heating, greenhouse heating, aquaculture, pond heating, agriculture drying, industrial use, cooling, snow melting, bathing, and swimming. Advantages of direct use are a widespread resources available at economic drilling depth and the use of conventional well drilling, heating and cooling equipment. A basic direct use system often applied in low permeability reservoir. Usually heat exchangers are used in order to have a clean secondary fluid circulating through the user side of the system as the geothermal fluid usually is unsuitable for direct use. The main components of a direct use system are the downholes and circulation pump, pipelines and heat extraction and exchange parts. The downhole pumps used in direct use application are line shaft pumps. Piping for transmission and distribution are usually made from carbon steel, especially when temperature above 100 degrees are involved. Especially when temperature above 100 degrees Celsius are involved. Pipelines can be installed above ground or underground. Above ground installation allows for ease maintenance. However, damage from accidents or vandalism can be more probable. If pipelines are installed below ground, a protection by coating or wrapping is needed. Three different types of heat exchangers are suitable for direct use of geothermal energy, that is plate, shell and tube, and downhole heat exchangers. Plate heat exchangers are very common in geothermal application due to small size and fewer cost compared to other type of heat exchangers. In addition, plate heat exchangers can easily be increased or reduced in size if needed by adding or removing plates from the stack. In a special application, downholes heat exchangers are used. Many geothermal direct use systems are equipped with a peaking system or a backup plant for maximum load. Often, it is more economically to adapt the geothermal system to the base load and cover peak demand with the conventional boiler or other resources. In today's lecture, we have learned about the different technologies for extracting geothermal energy. Today's lectures end here. Thank you for listening.